Last time we have seen how to find the Laplace transform of piecewise continuous functions. And now in this lecture, we are going to apply it to linear constant coefficient ordinary differential equations with a piecewise continuous function on the right side. So we have a linear ordinary differential equation, with constant coefficients. So the most general form, antiderivative of y plus a constant a1 times m minus first derivative of y plus, and it keeps going up to the last coefficient, constant an times the function y. And on the right side, we may have a function of t, any function. And in this lecture, we are going to work on examples where this function g is only piecewise continuous. And from last time, recall from last time, that first of all, we write piecewise continuous functions using unit step functions, and the Laplace transform of a unit step function at the number a times a function f of t minus a. Let me emphasize this point. If you're using a unit step function, then you need to shift the function f by a units. So this is the Laplace transform is e to the minus a times s times capital F of s. What is capital F of s? It's the Laplace transform of the function small f of t, just t. Okay, so when you're multiplying with unit step function at a, you need to shift the function f by a units, and on the other side, in the s universe, when you take the Laplace transform, you don't shift your function. You take the same function, capital F of s, you just multiply it with the exponential function. Okay, so let's work out some examples. So the first example is to solve the initial value problem. The second derivative of y plus 3 times the first derivative of y plus 2y equal to u2t minus u1t. And initial conditions are y0 and y prime 0 are both equal to 0. Okay, so you don't need to, of course, you can just take the Laplace transform, but just to clarify what is going on, the function u2t minus u1t, what is this function? Now, first of all, when t is less than 1, both functions are 0. So this function is 0 if t is less than 1. And if t is between 1 and 2, then u2 is 0, u1 is 1, so the function is minus 1. And if t is larger than or equal to 2, both u2t and u1t are equal to 1, so the difference is 0. So the function on the right side for this differential equation is piecewise continuous. So for t between 1 and 2, it takes the value -1, including 1, but excluding 2. Otherwise, it is 0. You can take it to be 0 for t less than 0, or not. You can think about t starting from 0, doesn't matter. Okay, so the function on the left side only takes the value -1, the constant value, for t between 1 and 2, and otherwise it is 0. So we want to find a solution to this equation. Okay, so we are going to take the Laplace transform of both sides. So we are going to take Laplace transform of y double prime plus 3 times y prime plus 2y, and it's equal to the Laplace transform of the right side, which is, oh, I'm sorry, I made a mistake. I'm sorry. We can work it out this way, but to check whether we have the right answer from my notes. I'm sorry, u2 minus u3. Okay, so the function is 0 if t is less than 2. It is 1 if t is between 2 and 3. And it is 0 if t is greater than or equal to 3. I'm sorry, this was u3, not u1. So the graph then oops, not -1. +1. So at 2, including 2, excluding 3, the function is 1. Otherwise, it is 0. Okay. So the main thing is that the right side is a piecewise continuous function. You can, you can take u2 minus u1, but in that case, of course, your solution is going to be different. Okay, so on the right side, we have u2 minus u3. Okay, so remember the Laplace transform of the derivative. Laplace transform of the second derivative is equal to minus y prime 0 minus s times y 0 plus s squared times Laplace transform of y plus 3 times Laplace transform of y prime minus y 0 plus s times Laplace transform of y, and 2 times Laplace transform of y, and on the other side, Laplace transform of u2 minus Laplace transform of u3. Okay, but in the initial conditions, we are given that y prime 0 and y 0 are both 0. So on the left side, we have s squared plus 3s plus 2 times Laplace transform of y. And Laplace transform of y, remember, we denote by capital Y of s. And on the right side, remember the formula I gave you in the beginning, we did last time. A Laplace transform of U2 is e to the minus 2s times Laplace transform of 1. U2t is multiplied by 1. And remember, a Laplace transform of 1 is 1 over s. As minus u3 e to the minus 3s over s. Again, these we did Laplace transform of piecewise continuous functions, unit step functions. We did it in the last lecture. Okay. So to find capital Y of S, we need to divide by S squared plus 3S plus 2. So on the right side, we have two fractions, but the denominator is the same. So I'm going to write it this way. The common denominator, S, and from the left side, we need to divide by S squared plus 3S plus 2 times we have e to the minus 2s minus e to the minus 3s. Okay, now we need to solve our differential equation. We need to find the inverse Laplace of this function. And again, remember from previous lectures, we start by taking this rational function and dividing it into its partial fractions. So first we try to factor out s squared plus 3s plus 2. Can we factor it out? Yes, we can factor it out as s plus 2 times s plus 1, right? Plus 2 plus 3s, yes. So using partial fractions, we try to write it as a over s plus b over s plus 2 plus c over s plus 1. Now, a student wrote to me the other day asking about the easy way to find the numbers ABC. Remember, before this whole thing started, when we were doing lectures in class, I did show you this simple way. Okay, so what you do is to find the number A goes with S. So on the other side, you disregard S, and in the remaining terms, you put S equals 0. S because the denominator is S, and 0 makes the denominator 0. So when you put 0, you see in the denominator, you get 2 times 1, 2, 1/2. So A is 1/2. To find B goes with S plus 2. So you disregard S plus 2, and in the remaining terms, you substitute S equals minus 2, because S equals minus 2 makes the denominator S plus 2, 0. So S is minus 2, S plus 1 is minus 1, so B is also 1/2. And to find C, C goes with S plus 1, so you disregard S plus 1 and you substitute S equals minus 1, because that's what the denominator is 0. If you put S equals minus 1, S is minus 1, S plus 2 is plus 1, so C is minus 1/2. So this whole thing is 1/2 times 1 over S plus 1 over S plus 2 minus 1 over S plus 1. Okay? But to make sure, once you get your result, you should check whether this right side is really equal to the left side. Let me check my notes to see if oops, you see, I didn't do it right. why isn't, why, 1 over S, okay, let's see what I did wrong with S plus 2. Yeah, that's right, with C. I made a mistake with C. Oh, I see. For C, I put S equals -1. S is -1, and S plus 2 is +1. So C is -1, not 1/2. Right? C is -1. So here, since I factored out 1/2, here I take 2. Okay? So when you multiply by 1/2, it is -1. All right. So check that this side, 1 over S plus 1 over S plus 2 minus 2 over S plus 1 times 1/2 is really equal to 1 over S times S squared plus 3S plus 2. So check your work. Or another way you can do as we did previously. How? Okay. Another way to find ABC. On the right side, you get the common denominator. So A times S plus 2, S plus 1, plus B times S, S plus 1, plus C times S, S plus 2, divided by the common denominator, should be equal to the left side, 1 over S times S squared plus 3S plus 2. So this means the numerators must be equal. So A times S plus 2, S plus 1, S squared plus 3S plus 2. B times S, S plus 1, S squared plus S, plus C times S squared plus 2S should be equal to 1. So A plus B plus C times S squared plus 3A plus B plus 2C times S plus 2A should be equal to 1. This means A plus B plus C should be 0. 3A plus B plus 2C should be 0. And 2A should be 1. So we need to solve these three equations to find ABC. So from the last equation, we have A equals 1/2. So if we substitute it into the other two equations, B plus C is -1/2, and B plus 2C is -3/2. So if we subtract the second equation from the first equation, B minus B is 0, 2C minus C is C, -3/2 plus 1/2 is -1. So C is -1. And finally, B is -1/2 minus C. So -1/2 plus 1, it is B is 1/2. So finally, you have A equals 1/2, B equals 1/2, C equals -1. Of course, the same as we found above. So you can use either way. This is maybe the most certain way, and it works for any kind, because the other way, this way only works when we have only linear factors. So if you have something like s squared plus 1, a second degree factor in the denominator, this method doesn't work. It only works for linear, meaning first degree terms in the denominator. So the other method is more sure. But for our example, this means our fraction 1 over s times s squared plus 3s plus 2 is 1/2 over s plus 1/2 over s plus 2 minus 1 over s plus 1. Right? A is 1/2, B is 1/2, C is minus 1. Okay, now to find the inverse Laplace of this fraction, this means we take the inverse Laplace of each term separately. All right, so 1/2 times inverse Laplace of 1 over s is 1, plus 1/2 times inverse Laplace of 1 over s plus 2, e to the minus 2t, right? Laplace of e to the at is 1 over s minus a, remember. And you can think of 1 as e to the 0. S means s minus 0, so inverse Laplace e to the 0 times t, which is e to the 0, which is 1. All right, so minus 1 over s plus 1 e to the minus t. All right, but what we need to do is, so let me give this function a name. Let me call this function h. Okay. Now we are trying to find inverse Laplace of, remember, what was our original function, capital Y. Where is it? Yes. E to the minus 2s over s squared plus 3s plus 2 minus e to the minus 3s over s squared plus 3s plus 2. Okay. Now, this function is, okay, take e to the minus 2s. This is the Laplace transform of, since I have e to the minus 2s, I need to take unit step function u2, and in front of it, I need to take the function. Which function? The function whose Laplace transform is 1 over s squared plus 3s plus 2, which is the function h, right? Laplace transform of h is 1 over s times s squared plus 3s plus 2, all right? So here I need to take h of, since I have u2, unit step function at 2, I need to take t minus 2. And similarly, the other part, e to the minus 3s over s squared plus 3s plus 2 is the Laplace transform of u3t. And since I have why u3? Because I have e to the minus 3s. And since I have u3 in the function h, I need to shift by 3. So if I combine the two, oops. Oh, oops. Wait. Yes. Okay. So if I combine these two, inverse Laplace of e to the minus 2s over s squared plus 3s plus 2 minus e to the minus 3s over s squared plus 3s plus 2 is the first one. I have u2t in the function h. Remember the function h. Here it is. In the function h, instead of t, I need to take t minus 2. So 1/2 plus 1/2, I can't see the power of e. Yeah, 1/2 e to the power minus 2 times t minus 2. In parentheses, we are replacing t with t minus 2. Minus e to the minus t minus 2. And minus, for the second one, for the second part, I have u3t times, and now in the function h, I need to take t minus 3. So 1/2 plus 1/2 e to the power minus 2 t minus 3 minus e to the minus t minus 3. So this is my solution. And of course, the solution itself is only piecewise continuous because in the original differential equation, the right side is piecewise continuous. So we expect, we can't expect to get a continuous solution. For a continuous solution, the result of the left side should be also continuous, but on the right side, we have a piecewise continuous function. So the solution in this case is only piecewise continuous. Well, okay. This is a technical point. So technical point. It is not, if you don't understand it, don't worry about it. But in order to be complete, I should tell you this. Okay, technical point. On the left side of the equation, we have the second derivative of y. So to have the second derivative, the first derivative and the function must be continuous, so that they have derivatives. Okay? So when I say the solution is piecewise continuous, is not quite correct. The solution y above is continuous and differentiable. Its derivative y prime is also continuous. But the highest order, y double prime, is only piecewise continuous. We can't expect, because the initial conditions are only for y and y prime. And also in the original equation, on the right side, we have piecewise continuous function. So something on the left side should also be piecewise continuous. And the only thing left is the second derivative, because the first derivative cannot be piecewise continuous, because in that case, there wouldn't be any second derivative at the point where the first derivative is not continuous. But on the left side, we do have the second derivative, so we need a continuous derivative. Okay? As I said, this is only a technical point. So this is always going to be the case. Up to all derivatives up to the highest derivative are going to be continuous, but the highest derivative, which appears in our equation, is going to be only piecewise continuous. Those of you who are interested can check this out with this function, how we write this solution using unit step functions. If you want, you can write it in the open form. Remember the definition of U2 and U3. So this function, I'm going to use the notation, the function h. The solution is U2 times ht minus 2 minus U3 times ht minus 3. So it means the function is 0 if t is less than 2. It is equal to h of t minus 2 if t is between 2 and 3. And ht minus 2 minus ht minus 3 if t is greater than or equal to 3. Because when t is less than 2, both u2 and u3 are 0. When t is between 2 and 3, u2 is 1 and u3 is 0. And when t is greater than or equal to 3, both u2 and u3 are 1. Okay, so this is the more open form for the function yt. So you can check that y is continuous and differentiable at the points t equals 2 and t equals 3. Y prime is continuous at t equals 2 and t equals 3. But y double prime is not continuous at t equals 2 and t equals 3. Okay, but you don't have to. This is only for those who are interested. Not for all of you. I don't expect this. I don't expect all of you to understand this technical point. Only for those of you who are interested, you can go ahead and check this. For us, this is going to be the answer. That's it. We are done, finished with the example. Okay, now I know these examples are kind of long and tedious, but once you know what you are doing, it is routine. Okay, and the main thing is to remember. Main thing is that when you're taking a unit step function, the function in front of it should be translated, shifted by a. And on the other side, we don't shift the Laplace transform of f. Capital F stays at s, but the one on the t world should be shifted by a. All right, now next example, example 2. It is an example which involves something we did earlier. Remember, as an application to mechanical systems, we considered models of spring mass systems. And now, as in this example, we consider a spring mass system where the external force is piecewise continuous. Okay, so what is the problem? This problem, by the way, is the same problem as in the lecture notes. I don't remember, did I share lecture 23? If not, I'm going to share it in a minute. So the lecture notes, not the notes of this video lecture. You know, I have two types of lecture notes in ODTÜ class. One, the lecture notes from last semester by Özgür Kişisel, and two, the video lecture notes of these videos I do. Okay, so I mean the lecture notes, the same example. Okay, so suppose that we have an undamped spring mass system initially at rest. This part is for the initial conditions, where the object has mass equal to 1 unit, and the spring constant is 4 units. Initially, there is no external force on the system. Starting from time t equals 3, up to time t equals 6, an external force linearly increasing from 0 to 9 units is applied to the system. Afterwards, the external force decreases linearly from 9 units to 0 units. Nine units to 0, from time t equals 6 to up to t equals 15. Up to time t equals 15. After t equals 15, the system is free again. Write a differential equation that models the system and solve it. Okay, so what is going to be what we are solving for? We are solving for the function y, function of t, which is the position of the object. And remember when we were doing in mechanical systems lecture, I don't remember the lecture number now. This was U, not Y, but we denoted by U, but now we are going to use U for unit step functions. So in order not to confuse the two, we denote it by Y. Okay, so we have in general for undamped systems, again, you need to go back and check the lecture on mechanical systems. For undamped systems, the equation is m times y double prime plus k times y equal to capital F of t. Here m is the mass of the object, k is the spring constant, and F is the external force. In our example, mass is 1 and spring constant is 4. Now, for the external force, we need to write a piecewise function. For t less than 3, external force is 0. For t between 3 and 6, the force increases linearly. So rate of increase it increases from 0 to 9. So 9 minus 0 divided by, it becomes 9 at time t equals 6 minus, it starts at time 3. So 9 over 3, so rate of increase is 3. That means the external force 3 times t minus 3, and at time t equals 3, the force is 0. So 3t minus 9. Let me see if I did this right. Yes, so time t equals 3, the force is 0, and time t equals 6, the force is 9 units. Okay, now for t between 6 and 15, the force decreases linearly. So rate of decrease, rate of change, I should say, because it's going to be negative since it's a decreasing rate. It becomes 0 at time 15, and initially it is 9. It becomes 0 at time t equals 15 and starts from 9 at time t equals 6. So this is minus 9 over 9. So rate of change is minus 1. So our function in this case, minus 1 times t minus at time, okay, which time you want to take? At time 15, the force is 0 again. So this is 15 minus t. At time t equals 6, force is 9. At time t equals 15, it is 0. So the external force then is 0 if t is less than 3, 3t minus 9 if t is between 3 and 15, and 15 minus t if t, 6. If t is between 6 and 15, and afterwards it is 0 again. Okay, so using unit step functions, we start with 0 plus the first unit step function is u3. So we take the function after t equals 3, 3t minus 9, minus the function for t less than 3, which is 0. The next one is u6. The function for t greater than 6, 15 minus t, minus the function for t less than 6, 3t minus 9. And plus u15. The function for t greater than 15 is 0, minus the function for t less than 15, 15 minus t. So this is, okay, from 3t minus 9, if I take out 3, 3u3t times t minus 3, plus u6t times minus t minus 3t minus 4t, 15 plus 9 plus 24, plus u15 times t minus 15. And I'm going to do one more thing. From minus 40 plus 24, if I take out minus 4, u6 times t minus 6. So when I take the Laplace transform of this function, it is going to be 3 times u3, so e to the minus 3s, Laplace transform of 1, minus 4 u6, so e to the minus 6s, and the function in front of it is already shifted by 6, u6 times t minus 6, so I just take the Laplace transform of t. Plus u15, so e to the minus 15s. Again, the function t is shifted by 15, so I take the Laplace transform of t. So 3 e to the minus 3s over s minus 4 e to the minus 6s over s squared plus e to the minus 15s over s squared. Remember, Laplace transform of t is 1 over s squared. Okay, so the Laplace transform of the left side of our equation. Now, what is our equation? Remember, mass is 1, so y double prime, and spring constant is 4 times y equal to f of t. So what are the initial conditions? Initially, the system is at rest. So both the position and the velocity initially, system is at rest. So both position and velocity are 0. Okay, now to solve, so the first part of the question is this equation and the function capital F we give above. Okay, now how to solve it? We take the Laplace transform of both sides. Since initial conditions are 0, Laplace transform of the left side, s squared plus 4 times Laplace transform of y. And the right side we did above. Let me, okay. 3 e to the minus 3s over s minus 4 e to the minus 6s over s squared plus e to the minus 15s over s squared. So the Laplace transform of the solution, capital Y of s, we just divide by s squared plus 4. 3 e to the minus 3s over s squared plus 4 minus I did a mistake, I think. Let me see. Of course, I'm sorry. This is also s squared because u3t, you see, it is multiplied with t minus 3. So t is translated by 3. So it should be Laplace transform of t again, not 1, because u3t is multiplied with t minus 3. I'm sorry. Yeah. Okay. So this is also s squared. So all the denominators are the same. Now, to find our solution, we need to take inverse Laplace of this function. So, as before, first we need to apply partial fractions to 1 over s squared plus 4. Okay, in general, this is how we should do this. S squared, we have the same linear factor s repeated twice. So we take a over s plus b over s squared. And then the factor s squared plus 4 is second degree. So in the numerator, we may have a first degree polynomial, cs plus d. And we cannot take the easy way out here to find a, b, c, d because the factor s squared plus 4 is not linear. It's second degree. So we need to obtain common denominators. So to get the common denominator, I need to multiply a with s times s squared plus 4. And I multiply b with s squared plus 4. And we multiply cs plus d with s squared. And this should be 1. So a s cubed plus b plus d s squared plus 4a anything else with s? This is s cubed and s, oh, I'm sorry, okay. Let's do this. So coefficient of s cubed, a plus c should be 0. Coefficient of s squared, b plus d should be 0. Coefficient of s, 4a should be 0. Constant coefficient, 4b should be 1. So from last two, we immediately get a equals 0 and b equals 1 over 4. And we use it in the first two, we get c equals 0 and d equals minus 1 over 4. So the result, 1 over s squared plus 4 is 1 over 4 times 1 over s squared minus 1 over s squared plus 4. And you can easily check that this is correct. All right, now, what is the inverse Laplace of 1 over s squared? Just t, right? And what is the inverse Laplace of 1 over s squared plus 4? Sine 2t, right? But if you have sine 2t, then in the numerator you should have 2. So it is 1/2 sine 2t. Right? Let me check. Okay. S squared plus 4. Yes. Okay. So inverse Laplace of the function 1 over s squared plus 4 is 1 over 4t minus 1 over 8 sine 2t. And the solution is the inverse Laplace of, let's see, what was it? What was it? Okay, inverse Laplace of three e to the minus 3s over s squared plus 4 minus 4 e to the minus 6s over s squared plus 4 plus e to the minus 15s over s squared plus 4. Okay, so if I call this function again by h, the inverse Laplace of 1 over s squared plus 4, okay, what's the inverse Laplace here? 3, because of e to the minus 3s, I have unit step function u3, but then I need to shift the function h with 3. Minus 4 u6, and I shift h by 6, plus u15, and I shift h by 15. Oh, it's going to be long. Okay. 3u3t times h of t minus 3. 1 over 4t minus 3 minus 1 over 8 sine of 2t minus 3. Minus 4u6 ht minus 6. So 1 over 4t minus 6 minus 1 over 8 sine 2t minus 6. And plus u15 h of t minus 15. So 1 over 4t minus 15 minus 1 over 8 sine of 2t minus 15. Again, a long term, but that's what it is. Okay, you may say, if this is part 1, what is going to be in part 2 of this lecture? Okay, in part 2, I am going to work out, again, an example where in the solution, we need to combine shifts on the right and on the left. So we are going to have exponentials both on, so we will have unit step functions, so we have exponentials in S, but also when we try to come back with inverse Laplace, again, we need to do some shifts. We need to multiply by exponential functions. So we are going to have a shift in S. So when we try to come back with Laplace inverse, we will have some exponential function in T. We will see. Okay, so in part 2, I'm going to do just another example. Just one example is going to be a long one. But I think it is important to see some long solutions to understand how things work out. Okay, so this is it for part 1.